Welcome to this class of dipole moment. Okay, in this class we are going to start with electric dipoles. Let us start with defining what is an dipole moment. Now we have already defined dipole moment as charge into the distance between the charges, and the direction we have considered from the negative charge to positive charge. But suppose we had lot of charges, positive, negative, positive, then we cannot just apply this definition. So let us define dipole moment in more general way. For example, let us consider the following case: a dipole which is in x and y axis. The negative charge is at a distance r minus and the positive charge is at a distance r plus. Let d vector be the distance between them. So if we write the charge, these are position vectors. If we write the charge and the position vector, this is the negative charge plus we have the positive charge, then this will be q r plus minus. Now see, this r plus minus r negative is, or r minus plus this d vector is equal to r plus vector. So this d vector is nothing but r vector, r plus vector minus r minus vector. So we will get q into d vector. Now see, this is the definition of dipole that we already know. It is also, this d vector is also directed from the negative charge to the positive charge. So we can define the dipole moment by using this definition, which can be applied to large number of charges. So for discrete charges, the dipole moment, here what we have done is we have taken the product of the charge and the position vector. So for discrete charges, we can write summation of qi into ri, which is the position vector, where I is from 1 to n. This is for discrete charges. And for continuous distribution of charges, we can write integration of dq into ri. This is for continuous distribution of charges. So this is the new definition or general definition of dipole moment. This definition we can apply to many many charges as well as continuous charge distribution. Now let us look at the next point. The next point is, if the net charge is 0, then the dipole moment is independent of the origin. Okay, what do we mean here is, we have defined dipole moment as the summation of the charge and the position vector, where I is from 1 to n. That means the dipole moment depends on the position vector, that is the position of the origin. So if the net charge is 0, if the net charge is 0, then the position of the origin can be taken anywhere. Now this will be helpful in solving many problems. First, let us see the proof. Suppose we have this charge distribution. We have this charge distribution in which we take a positive charge, and let us try to apply the definition of dipole moment to this positive charge. This positive charge is at a distance r1 from, let us say, this origin O, and at a distance r2 from this origin, let us say, O2. Now let us say this is O1. Now, according to our definition of dipole moment, the dipole moment will be Q into R1 in for O1 origin, and we can also define this as Q into R2 for O2 origin. Now, this vector D plus vector R2 we can always write as vector R1 from the triangle law of vector addition. So this vector R2 will be nothing but R1 vector minus D vector. This value we can put in the definition of, let us say this is P1 and this is P2, in the definition of this dipole moment for P2 as Q into vector R2. That means we can write R1 minus D vector, that is nothing but Q into R1 vector minus Q into D vector. Now Q into R1 vector is nothing but P1, and Q into D is 0 because there is no charge at this place. There is no charge at this place, so Q is 0 there. So Q into D becomes 0. So we have proved that if the net charge is 0, then we can take the origin anywhere we want, or the dipole moment is independent of the origin. Next point that is going to help us solve lot of problems is, if the origin is symmetric, the dipole moment is 0. Let us try to understand this point. What do you mean by symmetry? Let us consider a square of side A. Now, if we take the origin at the center, now see the net charge is equal to 0. There are two positive charges and two negative charges, so we can take the origin anywhere we want. Now, if we take the origin at the center of the square and we go in opposite directions, I go in opposite direction, I will find same charges. This condition is said to be origin is symmetrical. That means in opposite directions same type of charges are present. If I go in this direction, negative charges are present. If I go in this direction, positive charges are present. That means the origin is symmetrical. Therefore, here I can say the net dipole moment is equal to 0. We can see from the directions also. Here the dipole moment is directed downwards, whereas here the dipole moment is directed upwards. If we add them, it will become 0. If we take horizontally, the net dipole moment on the upper side is directed in this direction, on the lower side it is directed in this direction. So in both the cases, if we take, whether we take horizontally or vertically, the net dipole moment we are going to get 0. So this result will be very helpful. That is, if the origin is symmetrical, that is same charges are present in opposite direction, then net dipole moment will be 0. Now let us use the principles we have learned to solve the problems. We have learned two principles, that is net charge is equal to 0. Then the choice of the origin, the dipole moment is independent of choice of origin, and second we have learned is that if origin is symmetrical, then net dipole moment is 0. Net dipole moment is 0. Okay, see the following example. In the following example, we have two charges plus q charge placed at minus a and minus q charge placed at minus a and plus q charge placed at plus a, and they have asked us to find the dipole moment at this x and y. Now they are saying if the origin is moved to the point x and y, then what is the dipole moment? Now see, here in this case the net charge is 0 minus q and we have another plus q, so net charge is 0. That means the choice of the origin will not matter, so we can take whichever origin we want. So we'll take the origin which is easier. Suppose we take the origin at this negative charge. If we take the origin at the negative charge here, then this positive charge will be at a distance a plus a, that is 2a. So the net dipole moment, and it will be in this direction. So the net dipole moment we can write as q minus q charge which is at the origin, so it will be 0, and plus q charge which is at a distance of 2a. It is in, let us say, a cap direction, so we will get the net dipole moment as 2qa I cap. This will be the net dipole moment that is given in choice number B. Okay, let us see another example. In this example, they have given a minus q charge which is distributed over this sphere, where a positive charge q is placed at the center, and there is a negative charge distributed over this ellipsoid, and here also a positive charge is placed at the center. Now, with respect to the origin of the coordinate system, which of the following statement is correct? Now, from the question itself, we can write in both the cases the net charge is 0. So the choice of the origin is not going to matter. Also, if we consider the sphere, with the positive charge at the center, and if you go in the opposite direction, what you are going to get is a negative charge and a positive charge at the center. Also, in the case of ellipsoid, you have a positive charge at the center, and if you go in opposite directions, you are going to get a negative charge. That means in both these cases the net dipole moment is going to be 0. So they have given us net dipole moment is 0 in both the cases, and p is 0 in case 1, not 0 in case 2, and other options. The first option will be the correct option. So the problems can be easily solved by applying these principles. Now let us look at the next principle that is going to help us calculate the dipole moment in many cases. That is, if the dipole moment also can be calculated in some cases by using the center of mass concept. So I can write the dipole moment is equal to q total, the total charge, and the position of the center of mass. Let us try to understand this by using an example. Suppose we are asked to calculate the dipole moment at the origin for the following charge distribution. We know that the dipole moment, now this is a continuous charge distribution, so we are going to use dq into ri, that is the position vector. Now here dq will be equal to lambda dl, or we can write this as lambda into r d theta, where d theta is the small angle made by the length element. This small angle is d theta, and this we can consider to be as our theta. Now let us apply this. P is equal to lambda and r will be constant, they will come outside the integration. We will have d theta into r, the position vector. Now r we can write in the Cartesian coordinate system as r cos theta I cap plus r sin theta j cap into d theta. I have taken this r vector and this theta angle and taken the components in x direction and in y direction. In x direction you will have r cos theta I cap, in y direction you will have r sin theta j cap. So now we can integrate this. Here the limits of integration will be from 0 to pi. So lambda into r, we can take this r also outside, we'll get lambda r square cos theta d theta from 0 to pi, and plus we will have integration of 0 to pi of sin theta d theta. That means we are going to get sin theta from 0 to pi and minus cos theta from 0 to pi. Okay, this term is going to become 0 because sine is 0 at both this pi and 0. So what will be left is minus cos pi is minus 1, cos 0 is minus 1. So we will get lambda r square, this will be 2. Now let us put the value of lambda. Lambda will be q divided by